Welcome to qnawire.
Welcome to Digital Tea with Mr. E, where we see what's brewing in the world of physics education. Today we're going to take a look at a quantum mechanics style problem, algebra-based. This one deals with the Heisenberg uncertainty principle. The gist of the problem is that we are to imagine that we are in another universe where Planck's constant is a far larger number at 0.663 joule seconds, and there we got two students having a catch with a ball. The students are 12 meters apart. The ball has a mass of 0.25 kilograms. If quantum effects were not being considered, the ball would be moving at, we would know for sure the ball is moving at 6 meters per second. However, with the Planck's constant being so large, the person that's receiving the ball understands that the ball's initially starting in a 125 centimeter cube. And they know that with certainty, although the fact that there's a cube there leads to the uncertainty. Basically, this is Heisenberg's uncertainty principle, in that you can know either the momentum or position of an object, but the more you know one of them, you know less of the other one. So the key to start with this solution is that box of 125 cubic centimeters. If we take the cube root of that, that would give us dimensions of 5 centimeters by 5 by 5 centimeters. And if I consider that the box is completely centered around the head of the person that's going to be receiving it, this distance across the whole top would be 5 centimeters. So how I'm going to use that in my problem is I'm going to divide that by 2, meaning the ball could end up landing it could be 2.5 centimeters in front or behind. So you have 2.5 centimeters, and then put that in a metric. That would be a delta x of 0.025 meters for the uncertainty of the original starting position of the ball. So now, with that as an acceptable uncertainty, we're going to then see what the correlated uncertainty in the momentum is equal to. So we can express that as a change in momentum is equal to Planck's constant over 4 pi times the uncertainty in the position. Substituting our numbers in, we would have 0.663, 063, my bad, put a 0 up there, 0.663 over 4 pi times 0.025. Run that through the calculator, and that gives us an uncertainty in momentum of 0.211 kilogram meters per second. So now, that would be the first part of the question, the uncertainty in the momentum. The second part of the question wants to know by how much could the ball miss the target by, where the target's 12 meters away. The approach for that one I looked at is, if I take a look at this uncertainty in momentum and I consider it equal to the standard momentum equation of mass times velocity, or in this case delta velocity, I want to find the uncertainty in the velocity. So that would be a delta v equals delta p over m. So run the numbers through that, get our 0.211 over 0.25, was it? Yeah, 0.25 kilograms. And that gives us an uncertainty in the velocity of 0.844 meters per second. Now, let me write in a different color. If I wasn't considering the quantum effects, I would say that the velocity is equal to displacement over time. and we know everything but the time. So if I solve for time, that would be displacement over velocity, and we would know that it goes 12 meters, and it does so with a speed of 6 meters per second, so that gives us a time of 2 seconds. I'm going to say that this time is important because the 12 meter per second is nowhere near the speed of light, so therefore we should not be dealing with any relativistic effects of time dilation. As a result, even in the quantum mechanical sense, this time would be realistic, and it could be something that we could use over with our trying to figure out our displacement error for the ball getting there. So we're going to stick with this 2 seconds. So now back over to our regular solution. If I take a look at the velocity of 6 meters per second, and I add 0.844 to it, and I subtract 0.844 to it, that would give me 6.844 and 5.156. Now the reason I did this is the variance is 0.844, so it could be greater than 6 or less than 6 by the 0.844. So now I'll just multiply each of these by 2 because we had 2 seconds, and that should give me 2 different displacements. So the first displacement would be 13.68 meters, and the other one would be 10.31 meters. So the ball is going to go as far as 13.68 or as close as 10.31. So if I subtract them, that would give us a uncertainty in the displacement. I'll note that as delta du of 3.37 meters. Now if you consider that in a diagram, so here is our person that is receiving the ball, and it's there at 12 meters, standing there. However, this ball could be anywhere between the 13 and the 10 in this distance of 3.37 meters. So if I divide that by 2, that would give us a possible error of 1.685 meters, meaning the ball could end up 1.658 meters in front of the person or 1.685 meters behind the person. I guess if I was going to stick with significant digits as I went throughout, just looking at it over quick, everything looks to be, the limiting one looks to be 2, so I guess the more proper answer would be 1.7 meters. All right. Thanks for learning with me. I have certainly enjoyed learning with you. Have a good day.